Great. Welcome to the new week. I hope the test week went well and everything went according to plan. So we've finished grading and I'll post the grades a bit later today. I'm just still doing some processing on the data and just seeing what I can see from how the test went. Okay, so let's start off with just recapping briefly what we did last week so that we can just make sure we start off all on the same page. We are now busy with a new topic of function approximation. So last week we ended off with a strong form of solid mechanics boundary value problem with 15 unknowns and 15 field functions that we needed to approximate. So you feel free to go back to that video to just recap. But towards the end of last week, I just quickly actually already covered this slide. I'm just going to recover it again just to get the ball rolling. So essentially, what we have is we have some function v of x. Okay, and there's just the explicit form of it. But what we want to try and do is to try and approximate this v of x with another function. And the other function we're going to use to try and approximate it is this g of x with three coefficients a, b, and c. So it's just a pure quadratic. And you can see that this won't be able to exactly describe this because this has got a fourth order term. So there's a quadratic squared. X squared, two of them. So that's a fourth order term that we have got there. And so what we're going to try and do is to see what is the best fit we can do with this quadratic to try and approximate this function. Okay. So the two approaches that we carved out was to say, well, the one that we know from sort of NPR 213, we've done sort of in our first year linear algebra, is the discrete approach, where we say, let's evaluate this v of x at a couple of x's. Okay, let's evaluate it, and then for each of those x's, we can calculate the corresponding v of x1 and v of x2, v of x3, for instance. And we can put them all into a sort of a system of equations. So what this is just is the first equation here is a, so this a, b, and c will multiply with the columns again. So each a's will multiply with the first column, b with the second column, and c with the third column. So what stands there is a x1 squared plus b x1 plus c is equal to v of x1. So all it is substituting into this x1. Okay, and then that's this left-hand side. And on the right-hand side, I'm substituting into this expression, x1, to get that right-hand side. Okay, so that's all we're doing. We're doing 6 times. Now I've got a system where the A is known, this or this matrix here is known, this right-hand side is known. The only things that are unknown are these A, B's, and C's. Okay, so that's one way of doing it, is to look at discrete number of points. Alternatively, I could say, let's look at infinite number of points. And the way we can do this is to say, let's do a continuum integral approach. And in this approach, what we do is we just say, let's take the g of x and subtract from that the v of x and get the residual out. Okay, so this residual is now a function of x, a, b, and c. There's the v of x and there's the g of x. I can square it so that something is always positive, and then I can say, let's integrate over the domain of x from 0 to 1.5. And you can look carefully here. What is that length there? It's 1.5 meters. There's no units there in this graph, but it should just be meters there. But essentially, I end up with an error that is now only a function of a, b, and c, because if I integrate an expression of x over x, that's a definite integral, I end up with only with the other variables that are unknown. The x's become all constants. Okay, so now I've set with an expression of a, b, and c. What we see is these two systems are very similar. This is a system of equations that I need to solve, linearly overdetermined. And here's a system that I need to solve, or something I need to solve that's an error that has got a, b's, and c's in there. And so let's see how we can go about solving that. So this is just a quick overview. I'm going to stop this video and then I'll start the next lecture, because now we're going to start looking at a bit more detail. How do we solve this linearly overdetermined system of equations, and how do we go about solving this sort of error squared term, or this error term that is sort of a residual squared. Okay, let's learn that. Thank you.